The year 1947 saw the publication of Dennis Gabor's seminal work, Microscopy by Reconstructed Wavefronts, a paper that outlined a novel approach to microscopy, an approach that would eventually be known as holography. This essay undertakes a comprehensive and critical evaluation of the arguments, claims, and methodologies presented within this foundational text. It delves deeply into each section of the paper, scrutinizing the evidence provided and assessing the logical soundness of Gabor's reasoning. The primary focus remains on the internal consistency and the merit of the arguments as presented in the original publication, acknowledging historical context and subsequent developments only insofar as they illuminate the analysis of its core tenet. Section 1, Introduction and Statement of the Problem. Gabor begins by acknowledging the limitations inherent in existing microscopy techniques, particularly the spherical aberration present in electron microscopes. He states that these aberrations limit the resolution achievable, preventing the observation of finer details in microscopic specimens. He proposes a two-step imaging process as a potential solution, a process that he terms microscopy by reconstructed wavefronts. The central claim here is that by recording both the amplitude and phase information of a wave diffracted by an object, one could subsequently reconstruct a complete and accurate image, even in the presence of aberrations. This initial section lays the groundwork for the subsequent arguments, presenting the problem and hinting at the revolutionary solution which he will elaborate upon. It is crucial to note that Gabor is not simply suggesting an improvement upon existing methods. He is proposing a fundamentally different approach to image formation. The strength of this opening lies in its clarity in defining the problem and its bold assertion of a possible pathway forward. Gabor frames the issue as needing a totally new avenue in order to escape the inherent limitations of the physical equipment present at the time. Section 2. The principle of wave-front reconstruction. This section delves into the theoretical underpinnings of the proposed method. Gabor describes the process of illuminating a transparent object with a coherent wave. The wave is then scattered, creating an object wave, and the object wave combines with the reference wave to produce an interference pattern on photographic film. This interference pattern, he asserts, captures both the amplitude and phase information of the object wave. The claim is that this recorded interference pattern, the hologram, contains sufficient information to reconstruct a faithful replica of the original object wave. Gabor uses, without explicitly stating, a mathematical analogy to Fourier analysis, suggesting that the hologram is effectively a complex diffraction grating. He argues that when the hologram is illuminated, it will diffract the incident light, creating a reconstructed wave that is identical to the original object wave, in addition to a conjugate wave. A critical assumption here is the availability of a coherent light source. In 1947, truly coherent light sources were significantly less developed. Nonetheless, Gabor argues that the principle is sound, even if practical implementation presents challenges. The success of the entire concept hinges upon the fidelity with which the interference pattern can capture and subsequently reconstruct the wave front, requiring the recording medium to possess extremely high resolution. Section 3. Experimental verification with optical microscopy. Having established the theoretical framework, Gabor presents experimental results obtained using visible light. He describes a simple experimental setup involving a mercury arc lamp, a pinhole aperture to enhance coherence, and a conventional optical microscope. He creates holograms of various microscopic objects and demonstrates that these holograms can indeed be used to reconstruct images of the original objects. A key observation he makes is that the reconstructed images exhibit three-dimensionality, a significant advantage over conventional microscopy. He acknowledges that the reconstructed images can suffer from imperfections, such as the presence of the conjugate image and speckle noise, but argues that these imperfections do not invalidate the fundamental principle. The evidence presented is primarily qualitative, consisting of photographs of reconstructed images, a quantitative analysis of the image quality, such as a measurement of the achievable resolution, is absent. While the experimental results provide initial support for the theory, they are somewhat limited in scope and rigor. The success of the experimental verification, given the limitations of the equipment available at the time, is remarkable. The imperfections in the reconstructed images, while acknowledged, do highlight the need for further refinements in the technique. Section 4, Application to Electron Microscopy. Gabor extends his discussion to the potential application of wavefront reconstruction to electron microscopy. He argues that the same principle can be applied using electron waves instead of light waves. The key advantage, he suggests, is that electron microscopy suffers from severe spherical aberration, and that his technique will enable correction of the aberrations digitally to achieve resolution far beyond what is possible with traditional electron microscopy techniques. He does, however, acknowledges the practical difficulties associated with electron holography, such as the need for highly coherent electron beams and high-resolution recording media. This section is largely speculative, as Gabor did not have access to the technology required to perform electron holography at the time. The argument hinges on the assumption that electron wavefronts can be recorded and reconstructed with sufficient fidelity, an assumption that would require significant technological advancements for its verification. While the potential benefits of electron holography are significant, this section relies more on theoretical extrapolation than on experimental evidence. The foresight of Gabor in recognizing the potential of this approach is notable even in the absence of concrete experimental validation. The vision presented is a testament to Gabor's deep understanding of wave phenomena and his ability to extrapolate from optical to electron microscopy. Section 5, Discussion of Aberrations and Phase Contrast. This section focuses on the advantages of wavefront reconstruction for dealing with lens aberrations, particularly spherical aberration. Gabor argues that because the hologram captures both the amplitude and phase of the object wave, aberrations can be corrected during the reconstruction process. He also draws a connection between his technique and Cernight's phase contrast microscopy, pointing out that wavefront reconstruction can be considered a more general and powerful form of phase contrast imaging. The claim that aberrations can be corrected during reconstruction is a central tenet of Gabor's argument. By capturing the complete wavefront information, the effects of aberrations can, in principle, be computationally reversed. However, this requires accurate knowledge of the aberrations present in the system. The connection to phase contrast microscopy is also insightful, highlighting the ability of wavefront reconstruction to visualize transparent objects that do not absorb light but only alter its phase. Gabor emphasizes that his approach provides a more comprehensive solution than phase contrast microscopy, as it captures both amplitude and phase information. The discussion of aberrations is pivotal, as it underscores the potential of wavefront reconstruction to overcome a fundamental limitation of conventional microscopy. The recognition of the link to phase contrast microscopy is also significant, placing the work within the broader context of imaging techniques aimed at visualizing transparent objects. Section 6, Coherence and the Reference Wave. Gabor addresses the importance of coherence in obtaining high-quality holograms. He explains that a coherent reference wave is necessary to create a well-defined interference pattern on the recording medium. He discusses different ways of generating a coherent reference wave, such as using a point source of light or a partially coherent source with spatial filtering. He emphasizes that the quality of the reconstructed image is critically dependent on the coherence of the illumination. The argument that coherence is essential for successful wavefront reconstruction is undeniably correct. The interference pattern that formed the hologram is a sensitive function of the relative phase between the object wave and the reference wave. If the illumination is incoherent, the interference pattern will be blurred, resulting in a poor-quality reconstructed image. Gabor's discussion provides practical guidance on how to achieve sufficient coherence for holography, given the limitations of available light sources. The emphasis on coherence highlights a significant practical challenge in implementing holography. Particularly in the early days of its development, the techniques described for generating coherent reference waves demonstrate Gabor's ingenuity in overcoming these challenges. Section 7. The problem of the conjugate image. Gabor acknowledges a significant drawback of his technique, the presence of a conjugate image that overlaps with the desired image. The conjugate image is a twin image that is formed on the opposite side of the hologram from the true image. The problem is that the conjugate image degrades the quality of the reconstructed image and makes it difficult to obtain a clear view of the object. He proposes several methods for reducing the effect of the conjugate image, such as using off-axis holography or spatial filtering. Recognition of the conjugate image problem demonstrates intellectual honesty. The presence of this artifact is a significant limitation of the original inline holographic setup. The proposed solutions, such as off-axis holography, represent important advancements in holographic techniques. Off-axis holography, in particular, allows for the spatial separation of the true image and the conjugate image, greatly improving the quality of the reconstructed image. The exploration of methods to mitigate the effect of the conjugate image is a crucial step in making holography a more practical and useful imaging technique. Section 8. Resolution and information content. Gabor explores the factors that limit the resolution and information content of holograms. He argues that the resolution is ultimately limited by the wavelength of the illuminating radiation and the numerical aperture of the recording system, the same limitations that apply to conventional microscopy. He further argues that the information content of a hologram is proportional to the area of the hologram and the square of the resolution. The claim that resolution is limited by wavelength and numerical aperture is consistent with the fundamental principles of diffraction. This highlights that holography is not a technique that can circumvent the laws of physics, but rather a method for recording and reconstructing wavefronts with maximum fidelity. The discussion of information content is also important, highlighting the importance of recording a large hologram with high resolution in order to capture as much information as possible about the object. The analysis of resolution and information content helps to put holography in perspective, demonstrating its strengths and limitations in relation to other imaging techniques. The analysis provides design guidelines for optimizing holographic systems to achieve the best possible image quality. Section 9. Applications and future possibilities. Gabor speculates on the potential applications of wavefront reconstruction in various fields, including microscopy, three-dimensional imaging, and data storage. He foresees the possibility of creating three-dimensional displays using holography. He also suggests that holograms could be used to store vast amounts of data in a compact form. This section is highly visionary, anticipating many of the applications of holography that would eventually become reality. The prediction of three-dimensional displays is particularly prescient, demonstrating Gabor's deep understanding of the potential of holography to revolutionize visual communication. The suggestion that holograms could be used for data storage is also insightful, paving the way for the development of holographic data storage systems. The exploration of potential applications is a testament to Gabor's imagination and his ability to see beyond the immediate limitations of the technology. The envisioned possibilities helped spur further research and development in the field of holography. Section 10. Discussion of the limitations of the first experiments. Gabor openly acknowledges the limitations of his initial experiments. The primary limitations were the low intensity and poor coherence of the light sources available at the time, the presence of the conjugate image, and the lack of high-resolution recording media. He discusses ongoing efforts to overcome these limitations and improve the quality of holographic images. The acknowledgement of the limitations is a critical element of the paper. This indicates a deep understanding of the practical challenges involved in implementing holography. The limitations highlight the need for further technological advancements. The ongoing efforts to overcome these limitations demonstrate Gabor's commitment to the development of holography as a practical and useful imaging technique. The honesty in addressing these challenges provides a realistic assessment of the state of the art and sets the stage for future research. Section 11 Summary and Conclusions. Gabor concludes by summarizing the key principles of wavefront reconstruction and reiterating its potential advantages over conventional microscopy. He emphasizes the ability of the technique to correct for lens aberrations and to provide three-dimensional information. He expresses optimism about the future of holography and its potential to revolutionize various fields of science and technology. This section provides a concise and compelling summary of the main arguments presented in the paper. The emphasis on the potential to correct for aberrations is a key selling point for the technique. The reiteration of the three-dimensional imaging capabilities underscores the unique advantages of holography. The expression of optimism serves as a call to action, encouraging other researchers to explore the possibilities of this new imaging technique. The conclusion provides a fitting culmination to the paper, leaving the reader with a sense of excitement and anticipation for the future of holography. In conclusion, Dennis Gabor's 1947 paper Microscopy by Reconstructed Wavefronts presents a groundbreaking idea that would revolutionize the field of optics. While the initial experiments were limited by the technology of the time, the theoretical framework was robust and insightful. The paper clearly articulates the principles of wavefront reconstruction, acknowledges its limitations, and envisions its potential applications. The arguments presented are logically sound, and the evidence, while limited, provides initial support for the claims. The paper's enduring significance lies in its introduction of a fundamentally new approach to imaging, an approach that has had a profound impact on science and technology. Gabor's work demonstrated that a wavefront could in fact be frozen, captured and later resurrected. It is a testament to the power of innovative thinking and the transformative potential of scientific discovery. Despite the relatively primitive technology available at the time of writing, Gabor demonstrated a visionary capacity to foresee applications that would not become broadly available for decades. This paper remains a foundational text in the field of holography, providing inspiration for generations of scientists and engineers.